Hello, today we will continue with our chapter 18 on superposition of waves and standing waves. So let's remember quickly what we did in last lecture. What we did in last lecture is that we discussed if I have two waves traveling against each other, that is, they are traveling in opposite directions, at some point they will meet. And when they meet, there will be possibility to have constructive interference or destructive interference. And we said constructive interference, it's when the amplitudes meet and they give a higher amplitude. Destructive interference is when the amplitudes meet, but they give lower magnitude of the amplitude. Okay, so that's the idea we discussed last time. And we said, for example, in the example of a sound wave, if it's coming from a speaker, depending on the position of the listener, at some point he will listen the highest sound, and at other points he may not listen to anything. And we found the equations for that case. Today we are going to talk about one particular case, which is if I have two waves, but they are identical. So we are going to talk about two waves that are identical. That is, they have the same A and the same F, and they are traveling in opposite directions in the same medium. Okay, and we will find out. So again, there will be superposition, but we will find out that our superposition will produce an oscillation pattern that appears to have no sense of motion. So we will see something like what I've drawn over here. And if we look at this, we will think that it's not actually moving, while in reality, it is really moving. But to us, to our eyes, it will look like it's standing. That is, there is no sense of motion, okay? We're gonna talk about these particular points over here. These points, we call them nodes. That is, they are moving with zero amplitude. And these points over here, they are called antinodes. That is, they are vibrating at the highest amplitude. Okay, we're gonna find at what values of our K or our lambda these things happen. Okay, so the mathematical analysis, we have two waves. One of them is y1 equal a sine kx minus omega t. So this is going in the positive direction, if you remember. And y2 is a sine kx plus omega t, that is going in the negative direction. So notice y1 and y2 have same a, same amplitude. Same K, that is same wavelength. Same omega, that is same frequency. The only difference is that they are traveling in opposite directions. One is going in the positive direction, one is going in the negative direction. Now, the resultant wave will be y1 plus y2, which is a sine kx minus omega t plus a sine kx plus omega t. But we are going to use this formula over here, sine a plus sine b equal to sine a plus b over 2, cosine a minus b over 2. So according to our equation, a is kx minus omega t, and b is kx plus omega t. So now I will have y resultant is equal to 2. Here I have 2a. I have a here. So now I have 2 times a. So this is 2a sine of kx minus omega t plus kx plus omega t. Omega t and omega t cancel out. I will have 2kx over 2. So this is kx. Okay. Cosine a minus b over 2. So that's kx minus omega t minus kx minus omega t. The kx and kx cancels out. cancel out. I will have minus omega t minus omega t. That is minus 2 omega t divided by 2. So that's minus the 2 and the 2 cancel out. And I will have minus omega t. But I don't worry when I have a cosine function. Cosine the minus of something is the same as cosine the plus of the something. So I can remove the minus because cosine omega t is equal to cosine minus omega t. Okay. Okay, so I'm left here with y resultant is 2a sine kx cosine omega t. So this is the wave function of the standing wave. This expression is not expression of a single traveling wave. This is not like what we got before, y equal a sine kx minus omega t. Here it is in a standing wave. Each element oscillates in simple harmonic motion with the same omega, but with amplitude depends on the position, which is 2a sine kx. And how it will look like, it will look something like this. At some points, it's not moving at all. So depending on the value of x here, some points will not move at all. Some points will be at higher amplitude and other points will be in the middle. So let's analyze this further. Here I wrote the equation. Y resultant is 2a sine kx cosine omega t. Node is the point with 0 amplitude. Okay, so this is by definition, or 0 displacement. So these are the nodes. They are points with 0 amplitude or 0 displacement. They are in their place. Antinode are the points with maximum displacement. Okay, so they are with maximum displacement. These are antinodes. Location of nodes. So location of nodes. Remember here, this is the amplitude. So if I want location of nodes, implies location where amplitude resultant is equal to 0. So I will have sine of kx is equal to 0. And when does this happen? You have to remember sine function, sine of an angle equal to 0. What does it happen? It happens whenever kx is equal to n times pi, where n is equal 0, 1, 2, 3, etc. So for example, when n is equal to 0, when kx here equal to 0, sine 0 is 0. When n is equal to 1, that is kx equal pi, sine pi. So let's put this note over here. When n equal to 0, kx equal to 0, sine of 0 equals 0. If n equal to 1, kx equal pi, sine pi equal to 0. So this is correct. When n equal to 2, kx equal 2 pi, sine 2 pi. You can use your calculators if you don't believe me. Sine 2 pi is equal to 0, etc. So sine kx equal to 0 when n equals kx equal n pi, n equals 0, 1, 2, 3. Okay, but k is equal to what? K equal 2 pi over lambda. If you remember this, we came across it several times. So now I will put 2 pi over lambda equal to n pi. The pi and the pi cancel each other, and I do cross multiplication. So I get, this is 2 pi over lambda times x. Okay, kx equal to n pi. So I will get x is equal n times lambda over 2. Okay. So this is the location where I will get all my nodes when x is equal m lambda over 2. What is the distance between two nodes? One will be at, for example, 0. The other one will be at, so if n is equal to 0, x is 0. If n is equal to 1, x is lambda over 2. So what is the difference between these two? It is lambda over 2. Okay, so these are the positions, and here is what I've just said. So we will get the location of the nodes. Now let's get the location of the antinodes. Location of antinodes. So remember that antinodes are the points with maximum amplitude. Okay, so maximum amplitude. So location now of antinodes. I should have the A resultant equal maximum. That is, it will be plus or minus 2A or just 2A. Okay, so this is the maximum of this 2A sine kx. The maximum value is 2A. So when does this happen? This happens when sine kx is equal to 1. Okay, and this happens when whatever is inside the sine function is a multiple of pi over 2. So kx will be equal to 2n plus 1 pi over 2, where n is equal 1. Again, this is 0, 1, 2, etc. It's an integer. Okay, so again, let's try. If n is 0, this will be pi over 2, and sine pi over 2 is 1. So this is correct. If n is 1, this is 3 pi over 2. So if kx is a 3 pi over 2, again, the sign of that is 1. Okay, so why I put here 2n plus 1? This is just to make it 0, 1, 3, 5. So I make sure that I have pi over 2. If I just put m pi over 2, then for example, at value n equal to 2, this will be pi. And if this is pi, it will give me sine kx equal to 1. So here, just to make sure that I get these over 2's, okay? Pi over 2. Okay, so now we got the values. Now we have to get the values of x at which this thing happens. So k, again, I will put instead of it 2 pi over lambda times x is equal to 2n plus 1 pi over 2. And again, the pi and the pi will cancel out, and I will get x is equal to 2n plus 1 lambda over 4 this time. Okay, so I will get x is equal to 2n plus 1 lambda over 4, and the distance between two adjacent antinodes. So the distance between two antinodes, for example, n is 0. N is 0 will give me lambda over 4. N is 1 will give me n is 0 will give me x equal lambda over 4. N is 1 will give me x is equal to n is 1 here, so I have 3 lambda over 4. And 3 lambda over 4 minus lambda over 4 is 2 lambda over 4, which is again 2 lambda over 2. So the distance lambda over 2. However, the distance between one node and one antinode is lambda over 4. because you can do it by just taking n is 0. This will give you lambda over 4. However, in the other case, n is 0 would give x equal to 0. So the distance between 0 and lambda over 4 is lambda over 4. Okay. So here, these are two identical waves. You see y1 and y2, they are exactly the same. They're traveling in opposite direction. Once they interfere, there will be points where there are antinodes. There will be points where there are nodes. They don't move. So this is at time equal to 0. Then as they are passing, so at t equal period over 4, it will be like there is nothing. Okay, but here there is complete destructive interference. And then after another period over 4, it will look like this. So there will be maximum amplitude at these points, and there will be minimum amplitude at the nodes. Let's solve one simple exercise. This is taken from your book. Two waves traveling in opposite directions produce a standing wave. The individual wave functions are y1 equal 4 sine 3x minus 2 omega t. So notice here that I have a is equal to 4, k is equal to 3, and omega is equal to 2. Of course, here we have just to take care of the units. So this is 4 centimeter. This is radian per meter. This is radians per second. Okay, so y2 is exactly the same, but in the opposite direction. And they're saying that x and y are in centimeters. So that's why here I put a in centimeter and t is in seconds. Find the amplitude of the simple harmonic motion of the element of the medium located at x equal 2.3 centimeter. That is, I have to say y resultant is y1 plus y2. Sorry, let's repeat this. So y resultant is y1 plus y2. And this will give us 2a sine kx, which is a 3x, cosine of omega t, which is 2t. Okay, and the question is the amplitude. So we will say a resultant is equal to 2a, by the way, from here, it is 4. So 2 times 4 times sine of 3, and x, they are telling me it is 2.3. So this is equal to 8 sine 6.9. Just make sure that the calculator is in radian, and this will give 4.6 centimeters. Okay, this is part A. Part B. Find the positions of the nodes and antinodes if one end of the string is at x equal to 0. Okay, so one end is at x equal to 0. Now the nodes, location of nodes are at x is equal, it's at kx equal to 0, or x is equal to n lambda over 2. Okay, and how much is lambda? Lambda is, so this is n over 2 into lambda is 2 pi over k, right? So this is 2 times pi over k. And this is equal n over 2 times pi over k, which is 3. And this is equal 2 and 2, they cancel out, n over 2, and there is 2 up there, so they cancel out, and I will get n pi over 2. Okay, location of antinodes are at x equal 2n plus 1 lambda over 2. So again, I will just put instead of lambda 2 pi over k. So this is 2n plus 1 lambda, which is 2 pi over 3, 2 pi over k, that's it. So this is over 2, and this will give 2 divided by 2 will sorry, location of antidotes are at x equal to n plus 1 lambda over 4, not right. Let's check. Yeah, so antinodes happen at 2n plus 1 lambda over 4. So this is correct. So now I have 2n plus 1 into 2 pi over 3 over 4. So let's just correct the last thing. I will rewrite it. Okay, so I just wrote it in a better way. So location of nodes at x equal n lambda over 2. And lambda is 2 pi over k, which is 2 pi over 3. So then I just plug it instead of lambda, and I get location of nodes are at n pi over 3. Location of antinodes are at x equal to n plus 1 lambda over 4. So again, instead of lambda, I will put 2 pi over 3. So this will give me 2n plus 1 lambda, which is 2 pi over 3, and everything divided by 4. And this will give me 2n plus 1 lambda over 6. Pi over 6. Okay. And with this, I have reached the end of this problem and also the end of this lecture. Bye.